Hi everyone, I will now present my Lab 2 report. In this lab, we observed an object drop from rest and fall somewhat slowly. And in this case, I chose a crumpled paper ball as the object and drop it from 1 meter's height. And I chose the paper because it's light and the drag will have a higher effect on it and it will fall slowly. And we'll see an application of Newton's second law in this lab. We'll create two models, one with and one without drag, but both with gravity. And the result of this lab will show that the model with drag will stimulate the observation better. So here's our model. It's based on Newton's second law and uses the velocity and position update formula. And we can model the ball dropping in this graph. It's affected by a gravity pointing downward and a drag pointing upward. The gravity is given by this formula. We have a negative sign because it's in the negative direction of y-axis and a y-hat to make it a vector. And the drag is proportional to the square of the speed, which is the magnitude of velocity. And the b is the coefficient for the proportion. So we can use our tracker video to trace the observation. And we can also get our initial position and some movement here. And now is our code for our computational model. So in this code, we'll set up some mass, initial position, delta t things. And here one is important b here. For this coefficient, there's a lot of trial and error, and I finally find this best b that fits the computational model fits the observation the best. So, and we also have the gravity here and the drag here. So to calculate the drag, because the velocity only have a y component, so when we take the speed, its magnitude, we can just take its y component and square it. And the fnet is the addition, and here's the velocity and position update formula. So by running this code with b equal to 0 or with this value, can get the result for a model without drag and model with drag, shown by blue and orange line here. We'll notice the model without drag, the ball will somehow drop further. So let's discuss which model will predict the terminal velocity. Only the model with drag will predict the terminal velocity, because in this case gravity always exists. So we need a drag pointing up to balance the gravity to reach terminal velocity. So this is not possible for a model without drag. And in our case, the velocity will increase, and drag will increase correspondingly, and the gravity is a constant. So in the end, the gravity and drag will come to the same value and balance. And what if there's an initial velocity? We'll show that the terminal velocity will be the same regardless of the initial velocity. You can prove this by running the model and visualize the velocity as a function of time in the time versus velocity versus time graph. So we can set a bigger t, and now without initial velocity, we can print the velocity here. Now finally reach a velocity of -7, and even if we give it initial velocity, when we run it, we find out the final velocity is still -7. So to conclude this lab, we found out the model with drag simulates the actual situation of the dropping object better, and the object drop in the air is affected by a drag force proportional to the speed. which is actually air resistant, and the object will eventually reach a terminal velocity when the drag equals to equals to gravity, and the terminal velocity will not depend on the initial velocity. And that's all for my presentation. Thank you for watching.